Hello. Today we'll be looking at calculating equivalent resistance based on current flow. Now, circuit reduction is a technique that is used by many students in finding the total resistance of a circuit. In applying this method, the circuit is reduced moving towards the source. If circuit reduction is applied in finding the total resistance of the circuit shown, then we would be working from R5 going towards the source, hence from right to left. Let's see how we would go about reducing the circuit. The first step would be to reduce resistors R4 and R5 to form an equivalent resistance. So R4 and R5, which are in series, will be reduced to form an equivalent resistor. Next, we would reduce R3 and the equivalent resistors of 4 and 5 to form a single resistor, each time redrawing the circuit. So R3 and the equivalent resistance would now be reduced to form a single resistor. And then finally, all 5 resistors are combined. So from the previous circuit, we'll have the equivalent resistance of 3, 4, and 5, R2 and R1, all combined to form or to give us our total resistance. So if we were to assign values to these resistances, if we make R1 3, R2 11, R3 9, R4 14, and R5 4 ohms, and applying that or substituting that into the circuit that we had earlier, then the equivalent resistance for R4 and 5 would be 4 plus 14, which gives us 18 ohms. And this is so because, as we would have seen, R4 and 5 were in series, and so we'll simply add them. Next, we have the equivalent resistance of R3, 4, and 5 being equal to 6 ohms because we would have the equivalent resistance of 4 and 5, which is 18, being in parallel with R3. So we're using the formula here, product of resistors divided by the sum of resistances. All right, so 9 times 18 divided by 27, and that gives us 6 ohms. And then finally, we have all 3 resistances now in series, and so we will add them to give us the total resistance for the circuit, which is 20 ohms. Now, the key to circuit reduction is that with each resistor combination that we reduce to find an equivalent circuit or to find an equivalent resistance, we have to redraw the circuit. What if we could find the resistance without redrawing the circuit each time? And that's where writing what we refer to as a resistance equation becomes applicable. Now, yes, we are dealing with a simple network, but we're going to seek to write this equation, and we're going to use the current flow through the circuit in writing this equation and solving it, and see whether or not we'll get the same resistance as the circuit reduction method. And we'll be looking at the current flow as the current flows from the source. So while circuit reduction looks at reducing the circuit going towards the source, in this method, in finding the resistance, we have to look at the current flow away from the source. Now, in addition to looking at the current flow, we have some standards that we're going to apply in writing this equation. The first one is that when we use the term series, so if we say that two resistances are in series, we're going to represent series with a plus sign. Whenever we use the term parallel, we're going to represent that using two parallel lines. And then there's a phrase that we're going to be using, which is rest of circuit. Whenever I say rest of circuit, I'm going to open a bracket. So these are the three things we want to remember. Series, represented by plus, parallel, represented by two parallel lines, and rest of circuit, represented by opening a bracket. So let's get started. Now, by definition, or this is how we're going to define series. Two resistances, and I'm being specific using resistances and not necessarily resistors, and I'll explain later on. But two resistances are in series if the current leaving the first is the same current entering the second. Again, two resistances are in series if the current leaving the first is the same current entering the second. And for parallel connections, we are saying that a parallel connection exists if the current entering the point connecting these resistances divide. So if the current divides, then we know that the resistances are in parallel. So let's get cracking at writing our resistance equation. Now let's go back to the original circuit. And we're going to start by looking at the current leaving the source. So we're going to start with current I1. Now I1 and I2 are the same, meaning the current I1 will leave R1, and it is the current entering, not just R2, but it is entering everything back here. And what we're going to call that is rest of circuit. So what I know is that I1, yes, so we have I1 over here. So I1 is the same current that is entering the rest of the circuit. Now what did we say? So we're going to start first by just writing RT. Yes. And before we get there, I2, as we see, it splits into I3 and I4, which means that this branch will be in parallel with everything back here. Again, rest of circuit, which indicates that there's a parallel connection. All right, so let's get cracking with writing our equation. Now, we get started by simply writing RT is equal to R1. So let's write that. So RT is equal to R1. Why? Because that's the first resistor we encounter. The next thing we're going to determine is how is R1 connected with the rest of the circuit. And based on what we just showed, all the current leaving R1 goes to the rest of the circuit. Yes? So it means that they are in series. Okay. So the same current through R1 enters the rest of the circuit, which begins with R2. Going back to our convention, it means that R1 is in series with the rest of the circuit. And the very first resistor we see in the rest of the circuit is R2. Step 3. All the current leaving resistor R2 will enter the rest of the circuit, which means therefore that R2 is in series with the rest of the circuit. So we are going to have a plus sign and we are opening another bracket. So we're expanding our equation, and here we go. So R1 is in series with the rest of the circuit, and R2 is in series with the rest of the circuit. R2 plus open bracket. Next. The next resistor that we encounter is R3. So we're just going to write R3. And since the current divides between R3 and the rest of the circuit, then we're going to use our parallel lines. Now let's put those in. So we start again. R1 is in series with the rest of the circuit. R2 is in series with the rest of the circuit. And R3 is in parallel with the rest of the circuit. Next. The current I4 is the same as the current I5, thus making the next resistor, which is R4, being in series with the rest of the circuit, which ends with R5. So instead of putting another rest of the circuit after R4, because we are now at the end, we put the last resistor. So let's see how that looks. So we were up to R3 in parallel with the rest of the circuit. And the next resistor we see is R4, and it is in series with R5. And because I have now completed R5, I close all my brackets. And this is my resistance equation. Now, does this really help? Let's see. Now, if I substitute the resistor values, and I'm going to apply the mathematical principle of solving the innermost brackets first, the total resistance can be found. All right? So I'm going to look at the innermost brackets, and I'm going to put in all the values that we had earlier for our resistances. So I have 3 in series with the rest of the circuit, which consists of 11 in series with the rest of the circuit, which consists of 9 in parallel with the rest of the circuit, which consists of 14 in series with 4. Innermost brackets, it means that I'm going to start with 4 and 14, then I'm going to expand it to 9, then I expand it to 11, and then expand to 3. All right? So let's see how that works. The other thing I want to point out, that since we're dealing with only 2 resistors, and we mentioned it earlier, at no time will we have more than 2 resistances. So we can easily use the product over sum application. All right? Okay, so let's get cracking. Here are my resistances. So I'm going to start with the 4 and the 14. If I do that, because they are in series, I simply add them. I get 18. 18 and 9, I get 6. So that's 9 times 18 over 27. Okay, so that gives us 3, and that's 6 ohms. Okay, and then the 11 plus the 6 is 17. And then finally, 3 plus 17, which gives us 20 ohms. So RT is equal to 20 ohms. And there we have a resistance equation, and we're able to solve that equation to get our total resistance. In summary, we first need to determine the current flow away from the source through each resistance. Next, we want to apply the circuit conventions for series, parallel, and rest of circuit. And then finally, we want to solve the resulting equation by considering the innermost brackets first. And that's how we go about writing our resistance equation and by looking at current flow. You can visit our website and find other videos which will have examples for you to try. Thank you.